Welcome. In the last couple of lectures, we have been discussing the expanding universe and several important and interesting astrophysical consequences of such an expanding scenario. It's now time to confront the embarrassing question. We have known since 1929, since the prescient papers by Georges Lemaitre and then Hubble and Homerson, that our universe is expanding. But we do not know why it is expanding. All we can say is that it was expanding in the past, billions and billions of years ago, and so it's expanding today. Well, surely that's not a very satisfactory answer. In this lecture, we shall try to answer this question, or more specifically, we shall discuss the currently fashionable paradigm of inflationary universe. Before we begin, may I remind you once again of the concept of the critical density of the universe, which is predicted by General Relativity. It follows from Friedman's equation that this critical density is 3h squared divided by 8 pi g, where h is the present expansion rate of the universe, or the Hubble constant. Now, we introduce the notion of a density parameter omega, which is defined as the density of the universe divided by this critical density. So if the density is equal to the critical density, then omega is 1. Presently, we know from observations, a variety of observations, that the value of omega is 0.3. Now, what is included in this budget is the energy density of baryons and radiation, as well as energy density of the dark matter, which we do not see directly. So please remember that as far as we know from observations, we have concluded that the omega parameter of the universe is 0.3. So it is less than the critical density. Now, let me pose some extremely worrying questions that confront the standard Big Bang model of cosmology. The first question is, why is the universe so homogeneous and isotropic? Well, the PowerPoint is hanging a little bit. Fine. The second question is, why is the density of our universe so close to the critical density? The omega parameter corresponding to the critical density is 1, whereas observations tell us that omega is 0.3. Why is it so close to 1? Now, I'll explain to you why this is a serious worry. The third problem is the following. According to the several versions of the grand unified theories, which tries to unify the nuclear strong force, the weak force of radioactivity, and the electromagnetic force, there ought to be magnetic monopoles. If you remember, electric charges exist. The divergence of the electric field is related to charge density. But the divergence of B is 0. This is a statement that you cannot have magnetic monopoles. What happened to all those magnetic monopoles that would have been produced in the very early universe, the grand unified era? Finally, the question as to why the universe is expanding. Now, we'll come to this last question a little later. But let me try to first explain why the first and second are serious worries to the standard model of Big Bang cosmology. The first problem is known as the horizon problem. It is really a problem of the homogeneity of the universe. So I shall explain, it is also known as the horizon problem. Now, what is shown here is that the temperature distribution on the sky of the cosmic microwave background radiation. Now, this temperature is constant over the sky to 1 part in 10 to the power 5. Now, therefore, the question is, why is the temperature of the background radiation uniform or the same in all directions to a very remarkable accuracy? Now, let me try to convince you that this is a very serious problem. So, why is the universe so homogeneous and isotropic? Why is the temperature of the cosmic background radiation very nearly the same everywhere? The observed homogeneity of the cosmic microwave background temperature all over the sky implies that different parts of the universe were in causal contact in the distant past. They must have exchanged information, come to thermodynamic equilibrium so that the temperature will be the same everywhere according to the zeroth law of thermodynamics. Of course, we cannot see beyond when the universe was roughly 300,000 years, and that is, of course, the time of the last scattering or the time of recombination that I introduced to you in the earlier lectures. So why was the universe so homogeneous and isotropic at the time of the recombination, when the universe was 300,000 years old? Now, I would like to now convince you that different parts of the universe could not have been in causal contact with one another in the distant past. This simply would not have been possible. Because if you go back in time to the Planck era, when the time was 10 to the power minus 43 seconds, the size of the universe was roughly 2 or 3 centimeters, size of a ping pong ball. But the causal horizon size, that is the distance up to which you can communicate at the speed of light, was only 10 to the power minus 28 centimeters. Now, let us introduce the concept of the horizon size. Causal horizon size. It is the distance to which light can travel in the age of the universe at that time. Now, the universe is homogeneous isotropic on scales larger than several hundreds of megaparsecs. It is inhomogeneous in very small scales, but in a very, very large scale, it is homogeneous and isotropic. The present horizon scale, by that I mean the scale over which our universe is presently homogeneous, is certainly larger than c times t naught, where t naught is the present age of the universe, which is, say, 14 billion years or something like that. And if I multiply the speed of light by 10 billion years, I get 10 to the power 28 centimeters. So the statement I'm making is, the present universe is certainly homogeneous and isotropic over scales much larger than 10 to the power 28 centimeters. At the earlier times, this horizon scale over which the universe is presently homogeneous was, of course, smaller because the universe was smaller at that time. Therefore, the horizon scale would also be smaller. The horizon scale at an earlier time will be smaller by the ratio of the scale factors, Ri by R naught, where R naught is the scale factor of the universe today at T naught, and Ri was the scale factor of the universe at time Ti. So if I'm considering the time of the last scattering or the time of the recombination, Ti was 300,000 years, and Ri was the scale factor of the universe at that time. which you can calculate from Friedman's equation. Now that horizon scale at an earlier time ti will be related to the horizon scale at present ct naught multiplied by the ratio of the scale factors. So the horizon scale will be smaller. Yes, of course it will be smaller. But as we shall see, not small enough. So there it is once again. Now, at the time of the last scattering, or the time of the recombination, when the redshift of the universe was 1,000, this horizon scale was roughly 100 megaparsecs. In other words, the size of the causally connected region, the distance over which you could have communicated in 300,000 years, which was the age of the universe at that time, was roughly 100 megaparsec. And we know how far in distance a redshift of 1,000 corresponds to. So if I divide that 100 megaparsecs by that distance, I get an angular size, which is roughly 1 degree. So what I'm saying is that the causal horizon at the time of last scattering subtends an angle in the sky, which is roughly 1 degree. And I showed you this plot in the previous lecture. What is plotted is the power spectrum of the temperature fluctuations or the anisotropy in the temperature distribution of the microwave background radiation. And I said that observations tell us that the angular size subtended by this horizon at the time of the last scattering is 1 degree. Indeed, it is from this observation that astronomers concluded that the geometry of space is Euclidean and that the density of the universe must be precisely equal to the critical density. But we won't go back to the story at the moment. So I'm saying that the causal horizon, which is the distance over which you could have communicated when the universe was 300,000 years old, that distance, that scale, meter stick, subtends an angle of about 1 degree in the sky. So these are various 1 degree patches in the sky. All right? So there is no reason on Earth or elsewhere why the temperature of these regions should be the same, because they couldn't have communicated with one another. So the question is, why are the large numbers of causally disconnected regions? In other words, one could not have communicated between these regions at the speed of light in 300,000 years, which was the age of the universe at that time. So why is the temperature the same? Why do we live in a nearly homogeneous universe, even though there's been no time for different parts of the universe to communicate with one another and come to the same temperature? So that is the question. Now you may say, but look, maybe the homogeneity of the universe was achieved at an earlier time, earlier than 300,000 years. So maybe the universe was homogeneous and isotropic much earlier on. So don't work backwards, work forwards from that earlier time. No, that won't work, because the problem that I have just outlined gets worse and worse and worse the further back I go in time. I shall now try to convince you of that. So please listen to this argument very carefully. Now, what I have shown in this cartoon, this green sphere, is the size of the homogeneous region at an earlier time from which our homogeneous universe originated. In other words, if I extrapolate backwards in time, the size of our presently homogeneous universe to an earlier time, that is the size that I will get. And that size will be C T naught, the present time T naught, multiplied by the ratio of the scale factor. Now, what I've shown in the red sphere is the causal horizon at the earlier time T earlier or T initial, which is of course simply the speed of light multiplied by the age of the universe at that time, which is Ti. All right? Now, let's go back and ask, what would have been the state of affairs at Planck time when the universe was 10 to the power minus 43 seconds old? I would like to now convince you that at that time, in the Planck era, the size of the universe was roughly the size of a ping pong ball, table tennis ball. Whereas the causal horizon size was 10 to the power minus 28 centimeters. In other words, in 10 to the power minus 43 seconds, you could have only communicated up to a distance of 10 to the power minus 28 centimeters. Now, is this really true? Let me argue that it is true. As I said, one can calculate the size of the universe at the Planck time, size of the homogeneous part of the universe at the Planck time, by extrapolating back from today, T naught, according to Friedman's equations. Now, as I already said, the size of the homogeneous region of the universe at Planck time will be Ct naught, the present time, multiplied with the scale factor at Planck time divided by the scale factor today. Now, since the causal horizon at the Planck time is simply given by the speed of light multiplied by the Planck time, which is 10 to the power minus 43 seconds. So, here I have repeated, the size of the homogeneous universe at Planck era divided by the size of the causal horizon at the Planck era, extrapolated back from now using Friedman's equation, is of the order of the present time divided by the Planck time, multiplied by the scale factor at the Planck era, divided by the scale factor today. Well, do I know this ratio? I know that ratio because the ratio of the scale factor is the same as the ratio of the temperature of the universe at the two times. That is because, as I argued in the very first lecture on cosmology, RT is a constant. All right? This simply follows from the cosmological redshift formula and Wien's displacement law. So please go back and revise this portion. RT is a constant. All right? Therefore, the ratio of the scale factor at Planck time divided by the present scale factor is of the order of the temperature now, which is 3 degrees, divided by the temperature at the Planck era, which according to general relativity is 10 to the power 32 Kelvin. I told you how Friedman's equation predicts how temperature and time are related. Temperature is 1 over square root of T. And we knew what the proportionality constant was. Therefore, the temperature of the universe at Planck time was 10 to the power 32 Kelvin. Therefore, this ratio above, the size of the homogeneous universe at Planck time divided by the size of the causally connected region at the Planck era is 10 to the power 17, which is the age of the universe today, 10 billion years in seconds, divided by the Planck time, which is 10 to the power minus 43 seconds, and this ratio is 10 to the power minus 32, and that gives me a factor 10 to the power 28. And that is why I drew this picture. At Planck time, the size of the universe was a couple of centimeters, but the size of the causal horizon was only 10 to the power minus 28 centimeters, and therefore the size of the universe, the size of the homogeneous universe at Planck time exceeded the causality scale by a factor 10 to the power 28. Therefore, the radius of this little red sphere was 10 to the power 28 times smaller than the radius of the green sphere. Another way of saying that is already at the Planck era of 10 to the power minus 43 seconds, there were 10 to the power 84 causally disconnected regions. Where does this 84 come from? 28 multiplied by 3. So 10 to the power 28 whole cube will give me 10 to the power 84. So already at the Planck time, we have a serious problem. The temperature of the universe could not have been same everywhere because the universe at the time consisted of 10 to the power 84 causally disconnected regions. So going backwards in time hasn't solved the problem. So let's come back and look at the surface of law scattering, which we see in the distribution of cosmic microwave background radiation. And let me therefore ask this question once again. Why is the temperature of the background radiation uniform in all directions to an accuracy of a fraction of a millikelvin? This is known as the horizon problem. Now, there is a second problem with standard Big Bang cosmology, which comes from observations. This is known as the flatness problem. Why is this curvature of space zero? Why is the universe space is flat or Euclidean? The present density of the universe, as I said from observation, is 0.3 of the critical density. In other words, omega matter, baryonic matter plus dark matter plus radiation is only 0.3. But the power spectrum of the cosmic microwave background radiation tells us that the universe is Euclidean. Therefore, the density of the universe, according to general relativity, must be precisely equal to the critical density. Therefore, omega must be equal to 1. Although omega, due to matter, seen or unseen, plus radiation is only 0.3. Therefore, 70% of the energy density of the universe is unaccounted for. This is something that we have discussed earlier. So the question is, why is the density of our universe so close to the critical density, omega equal to 1, after 10 billion years? All right? If the density of the universe was a little more than the critical density, the universe would have collapsed on itself long time ago. There would have been no galaxies and there would have been no life on Earth to ask this question. On the other hand, if the density of the universe was very small compared to 1, then again we have a problem. Maybe galaxies wouldn't have formed in any case. So the question is, why is in the expanding universe expanding with tremendous kinetic energy, and why didn't it collapse long time ago? So these are two questions that can be asked. It seems as though the early universe was fine-tuned to make the universe what it is today. This fine-tuning is a matter of great debate today, and we shall perhaps touch on it in the final lecture of this series. Now, let me tell you why this is a serious problem. Omega is the density parameter at a redshift when the universe was at a redshift of Z. Omega at that redshift is related to omega now by this relation. There is a function of redshift. And that function f of z is 1 plus 1 divided by 1 plus z if the universe is dominated by matter, which it is, or it's proportional to 1 over 1 plus z whole squared if the universe was radiation dominated, which it was in the very early epoch. Now, why should omega depend on time? Very simple. As the universe expands, the density of matter decreases as 1 over r cube. Therefore, omega will decrease because the number density is decreasing and the energy density is decreasing. Therefore, to get omega of 0.3 today, which is very close to 1, requires fine-tuning of omega in the past. Omega now is pretty close to 1. In other words, this factor is pretty close to 0. Omega is only 0.3, is very small. In order for that to obtain, this omega at earlier times must have been fine-tuned. For example, if the initial conditions are defined at the Planck era, 10 to the power minus 43 seconds, then in order to get an omega of 0.3 today, omega at the Planck era must have been 1 to 1 part in 10 to the power 60. In other words, omega minus 1 must have been less than 10 to the power minus 60. In other words, the omega at Planck era must have been very nearly 1. Otherwise, you can't have an omega of 0.3 now. Well, if you look at a little later time, when the universe was 10 to the power minus 35 seconds, then omega minus 1 at that epoch must have been less than 10 to the power minus 53 seconds. So whichever epoch that you look at, you have a serious problem. In order to have an omega today, which is very nearly 1, you must have had an omega which was almost 1 when the universe was born. Now, so these are the two problems. The horizon problem, which is to understand the observed homogeneity of the universe, and the second is the flatness problem, which is to understand why omega is so close to 1. Observations tell us that omega is 0.3 as far as matter and radiation are concerned. So now, this is what I said before. At Planck time, t equal to 10 to the power minus 43 seconds, the size of the universe exceeded the causality scale by a factor 10 to the power 28. And that's what is shown in this picture. So, the size of the horizon at the Planck era divided by the size of the causally connected region in the Planck era is 10 to the power 28. When the universe was 10 to the power minus 43 seconds old. Now look at this expression very carefully. There is R Planck in the numerator, there is T Planck in the denominator. There is R naught in the denominator and T naught in the numerator. So there is this factor R over T. Now you can write R over T as approximately dr by dt, R dot, or the rate of change of scale factor with time, which is the expansion rate of the universe. Therefore, I can write this formula above. Size of the horizon at Planck era divided by the size of the causally connected region of the Planck era as the ratio of the expansion rate of the universe at the Planck era divided by the expansion rate of the universe presently. So, stated in words, the size of the observable universe at an initial time divided by the size of the causally connected region at the initial time must be equal to the expansion rate at the earlier time divided by the expansion rate today. All right? Fine. So this is just a restatement of this expression over there. So now, if gravity is always attractive, so far we have grown up with gravity always being attractive, then it will decelerate the universe. Yes, the universe is expanding, but the matter in the universe will be trying to pull the universe back. That's why the universe must be decelerating. Or R, as a function of t, must be a curve like this, which is a decelerating universe. Therefore, the size of the observable universe at an earlier time divided by the size of the causal horizon at an earlier time, which is equal to this ratio, is greater than 1. All right, fine. So this is the predicament we find ourselves in. The size of the observable universe, no matter how early you look, how further back in time you look, is always larger than the size of the causally connected region at that time. So the homogeneity problem remains as long as gravity was attractive in the past. So, if gravity is always attractive, it decelerates the universe. The scale factor of the universe, plotted as a function of time, is a curve like this. It is either t to the power 1/2 if the universe was radiation dominated, or t to the power 2/3 if the universe was matter dominated. So the expansion time at earlier time divided by the expansion rate now is always greater than 1. The universe was expanding faster before and slower now because the universe is expected to be decelerating. So we conclude that if the universe was always decelerating, if gravity was always attractive from the time the universe was born, then the homogeneity scale was always greater than the causality scale. So the problem remains all the way back to the beginning of the universe. So this is the dilemma. So to fix this horizon problem, the universe must accelerate earlier on, and it must expand exponentially. In other words, the expansion rate of the earlier time divided by the expansion rate at a later time must be less than 1, the rate. All right? So in some period, gravity must have acted as a repulsive force, resulting in an acceleration. So that is the green curve. So in order to solve this homogeneity problem, the only way to solve that is by postulating that at earlier times, when the universe was very, very young, for some reason gravity was strongly repulsive. It made the universe accelerate at a tremendous rate. Now, to allow for causal contact over the whole region, which is observed at the time of the last scattering, what do we observe at the time of the last scattering? The temperature is the same. Therefore, somehow or other, causal contact had been made in the distant past. That is why the temperature is the same everywhere. That is why the universe was so homogeneous and isotropic at the time of recombination. That would have been possible only if at an earlier time the universe had expanded faster than light near t equal to 0. Yes, you heard me rightly. The universe must have expanded faster than light. Now, what do I mean by that? I mean that the scale factor of the universe must have been proportional to t to the power alpha, where alpha cannot be 1/2, which is radiation-dominated era, or 2/3, which is matter-dominated era, but alpha must be significantly larger than 1, which corresponds to a universe expanding faster than light. Now, is this a violation of special relativity? Not at all. All we are saying is that the distance between any 2 points in the universe increase faster than light. You would violate special relativity only if you try to pass information between 2 points in the universe faster than at the speed of light. That is forbidden. Here we are not exchanging any information. We are just saying that space itself is expanding at a rate faster than the speed of light. Now, if such a phase had existed, we are not saying such a phase existed, because in classical physics, you don't have such a phase. But if such a phase had existed, the co-moving horizon size would have diverged. Remember, the co-moving horizon size is given by an integral over time of dt divided by the scale factor. Now, for that integral to converge, you integrate it from time 0 to some time t. Near t equal to 0, previously r in the denominator was either square root of t or t to the power 2/3. Therefore, the integral converged at t equal to 0. But if r is increasing as t to the power alpha, that integral will not converge. It will diverge at t equal to 0. That is another way of saying is that the horizon size would have diverged to a very large size. So let's consider this state of affairs around Planck time. Let us say this is the size of the causally connected universe. This is the distance over which light could have traveled in that time. Inside that, there is a small region which is homogeneous. The universe need not be homogeneous. The universe could have been inhomogeneous. But let us say one small region, the size of a ball bearing. This is the size of a ping pong ball. Maybe the size of a ball bearing, the universe was homogeneous and isotropic. What we are saying is that if that region could expand at a rate faster than the speed of light, then you will have the following situation. Then the homogeneous region of the universe could have expanded to a size very much larger than the size of the causality scale. Now please remember, this causality scale is determined by the speed of light, the distance over which light can travel in the age of the universe at that time. So we are talking about the possibility that the space itself expanded at a rate faster than at the speed of light. Classical physics does not have a plausible scenario for this to happen. So if I plot the expansion rate of the universe on the y-axis, r dot, this figure taken from a book, r is a, therefore it's a dot, as a function of time. So previously we said the universe started decelerating from t equal to 0. This corresponded to r of t being proportional to either square root of t or t to the power 2 by 3. So now what we are saying is that in the very early universe, there was an acceleration of the universe, and later on, the universe decided, okay, that's enough. We have solved the homogeneity problem, so let me now obey general relativity and Friedman's equation and follow this curve. So this is what we need. So the question is, how can gravity become repulsive? And how can gravity cause an acceleration, an exponential expansion of the universe? That is possible if the if the energy density of the universe has a component which comes from vacuum. This is known as vacuum-driven acceleration, which I already introduced when we discussed the acceleration of the universe, but let me state it once again. It never hurts to listen to it a second time. Now, this is the second of Friedman's equation. R double dot squared is minus 4 pi g by 3 multiplied by E plus 3p times R, where E is the energy density of matter, radiation, whatever there may be, and P is the pressure. We said in general relativity, P is also a source of gravity. The pressure is 1/3 the energy density. Therefore, pressure is energy density multiplied by 1 by 3. So as long as pressure is related to energy density, pressure will also contribute to gravity. And that is this 3. This 3 comes from the fact that pressure is 1/3 the energy density. Therefore, the equivalent energy density of pressure is 3 times P. That's what is written here. Now, if, as I discussed in the lecture on the accelerating universe, if E plus 3P is greater than 0, then because of the minus sign, there is deceleration. The universe decelerates. But if E plus 3P is less than 0, then we will have acceleration, because that minus sign and this minus sign cancel out. Now suppose you have vacuum, which is the dominant contributor to the energy density. Then, as I explained before, the pressure of vacuum is minus the energy density. The pressure of vacuum is minus rho c squared, whereas the pressure of ordinary matter is plus rho c squared. Therefore, E plus 3P is, if I use this expression, is minus 2E. And since energy density is always positive, this is less than 0. And therefore, vacuum energy causes acceleration. So let's now go back to Friedman's first equation. r dot squared minus 8 pi g by 3 rho r squared is minus the curvature factor k times c squared. Now, an exponential expansion will require an equation of state with negative pressure. As I said, an exponential expansion will require an equation of state with negative pressure. P is minus rho c squared. Vacuum has such an equation of state, as we discussed in the lecture on accelerating universe. Now, it may not be pure vacuum energy. There could be matter and radiation. But as the universe expands, since the energy density of matter and radiation decreases as 1 over r cube and 1 over r to the power 4 respectively, whereas the energy density of vacuum does not decrease, pretty soon vacuum energy will dominate over matter and radiation energy density. So the energy density of vacuum will dominate. Now, if the universe is dominated by vacuum energy, then the energy density is constant. It is not a function of time. It does not decrease. This rho here does not decrease with time. Therefore, I can integrate this differential equation very simply, as I told you to do, and I get r is proportional to e to the power ht, where h, which is the Hubble constant, is square root of 8 pi g by 3 multiplied by the energy density, which now is essentially the energy density of vacuum. Even if there had been initially some matter and radiation, its energy density would have dropped off to essentially zero. Therefore, the expansion of the universe will be determined essentially by the energy density of vacuum, and vacuum will cause an exponential expansion of the universe. Now, as I said before, unlike in classical physics, in quantum physics, vacuum has very rich physics associated with it. The Casimir effect that you might have read about is an example of that. Lamp shift in the spectrum of the ground state of the hydrogen atom is an example of vacuum fluctuation. So the energy density of vacuum is positive, but the pressure exerted by the vacuum is negative. Now, Einstein's cosmological constant is an example of vacuum energy. It is not associated with any matter, it is just a constant. Now, I made the argument possible by this thought experiment that if I have matter or radiation in this cylinder, then as the cylinder expands, as the piston goes up, the energy density of matter and radiation will decrease according to first law of thermodynamics because work is being done by the gas on the piston. That's because the pressure of the gas is proportional to the energy density. But in the case of vacuum, the pressure of vacuum is negative of its energy density, so it doesn't cost me any energy for this configuration to go to that configuration. There's more vacuum, therefore there's more vacuum energy. All right? So I can fix the horizon problem. If the universe was dominated by something like vacuum energy, we are talking of a real universe where there are particles and radiation. So we are talking about some not quite cosmological constant lambda of Einstein, but some form of energy which mimics vacuum energy. If we could have that, then we can solve the horizon problem. How to fix the flatness problem? Well, to get omega equal to 1 now requires fine-tuning in the past. As I said, since omega is only 0.3 now, very close to 1, then in the Planck era, it must have been close to 1 part in 10 to the power minus 60, or omega minus 1 at that epoch must have been less than 10 to the power minus 53. Now the problem can be solved simply if k, the curvature of the universe, is 0. If space is flat, if space is Euclidean. All right? You agree? It was 1 all along. So don't ask me any embarrassing question. It should be 1 now. So it's 1 now, near 1 now, because it was always 1 in the past. In fact, I'm making a prediction. It cannot be 0.3 now. It must be precisely equal to 1. Now, why would the curvature term be 0 in the past? Why should the early universe must have already been Euclidean? Well, so that's clear. Let's go on. So let's consider this curved surface. Let's consider a crumpled piece of paper. All right? Now, if I stretch this paper thousands and thousands and thousands and thousands of times, it will become flat. All the curvature will go away. So if I stretch this, each panel corresponds to stretching by a factor of 3. So I've stretched the sphere, expanded the sphere by a factor of 3, by another factor of 3, another factor of 3, and so on. An exponential expansion in the early universe, which made the universe homogeneous and isotropic, will automatically make the universe flat. It automatically remove all curvature. The curvature constant k must be equal to 0, or space must be Euclidean. So the flatness problem already gets solved. Therefore, if the horizon problem can be solved, if in the early universe the equation of state was such that the pressure is equal to minus rho c squared, then that exponential expansion, if it goes on long enough, will automatically solve the flatness problem. In fact, it will make a prediction that omega should be equal to 1. Therefore, astronomers, your measured value of omega may be 0.3, but go and look for the other 0.7, because I'm making a prediction that omega should be precisely equal to 1. And we know it is equal to 1. That's why the universe today is accelerating. So, some of the deeply disturbing problems with classical Big Bang cosmology could be solved if the universe experienced an early phase of exponential expansion over many e-folding times, such as would obtain if the universe was dominated by vacuum energy. All right, fine. Now, what I'm plotting on the y-axis is the scale factor of the universe as a function of time. This is 10 to the power minus 36 seconds. The significance of this particular time will become apparent in a minute. So what we are saying is that if the universe could have accelerated exponentially till around that time, and then decelerated according to Friedman's law of t to the power 1/2 or t to the power 2/3, then we would have killed 2 birds with 1 stone. We would have solved the horizon problem because the space would have expanded faster than at the speed of light, and therefore broken the causality barrier, and the size of the homogeneous universe could have become larger than the causality scale. And secondly, the geometry of the universe would be Euclidean. Now, in the year 1981, at MIT in Boston, Alan Guth, a high-energy physicist, who wasn't bothered at all by cosmology and the problems that we are discussing, was investigating a phase transition in the universe corresponding to the grand unified theory. Now, he found that this grand unified theory phase transition, which according to the theory of elementary particle should occur at a time around 10 to the power minus 35 seconds, could be one of those supercooled transitions, like supercooled water. I'll mention that in a minute, just wait. In which the universe was trapped in a metastable false vacuum, as the elementary particle physicists would like to call a metastable state. he discovered that while the universe was trapped in this metastable state or in this false vacuum, the universe would have exploded and expanded exponentially. So this was a possible solution to the cosmological crisis. A quantum phenomena, a purely quantum phenomena, seemed to come to the rescue of Big Bang cosmology. This is not what Alan Guth set out to do. Now let me say a few words more about this. This phase of exponential expansion of the universe is known as the inflation of the universe. So inflation is like inflation of our economy. If you read today's paper, the inflation is 7.4%. Inflation is a stage of accelerated expansion when gravity acted as a repulsive force. So what is this grand unified theory of phase transition? So let me explain this very briefly, because in the next lecture I'm going to discuss this in detail. When the universe was very, very young, even earlier than the Planck era, the hope is that all four forces of nature, gravity included, were unified into one theory. That the theory has not been constructed yet. Whatever it is, we know that already at the Planck time, gravity was a separate force, and it has remained separate till today. This is time going on the y-axis. But till a time of 10 to the power minus 35 seconds, in this period of the history of the universe, the strong interactions, the weak interaction, and the electromagnetic interaction were described by a unified theory, which is the standard model of physics which we already have. Fine. Now, what the standard model predicts is that at that temperature, the strong interactions goes its own separate way, and the weak and electromagnetic interaction go in a unified manner separately. So this is the phase transition where the unified theory of the three forces splits into two theories, one for the strong force and one for the electro-weak force. We will discuss this more in the next lecture. But let's proceed. So we're talking about a phase transition. Phase transition like water vapor becoming water, or water becoming ice, iron becoming ferromagnet, a metal becoming a superconductor, a liquid becoming a superfluid. These are all examples of phase transitions. Phase transitions are described by free energy as a function of what is known as order parameter. The order parameter in the case of magnetism would be the magnetization, spontaneous magnetization. I will discuss all this in detail in the next lecture, but let me proceed. The Guth phase transition is a first order phase transition, like the water-ice transition. The transition between a normal metal and a ferromagnet is a second order phase transition. Whereas the transition between water and ice is a first order phase transition, where there is a volume change and there is a latent heat. Now, what the theory of elementary particle physics tells you is that the grand unified theory phase transition, which must have occurred when the universe was 10 to the power minus 35 seconds old, was a first order transition. So in a first order transition, what happens is that the free energy jumps from a local minimum to a global minimum. But sometimes what happens is, let us say I'm cooling water. When the free energy of water becomes equal to the free energy of water in the form of solid water, then it jumps suddenly to the solid form, discontinuously. And that is the first order phase transition. And associated with that is the well-known latent heat and so on. But sometimes if the experimenter is very, very careful, water can be made to cool well below 0 degrees centigrade without becoming solid. This is known as supercooling of a liquid. Similarly, you can have a superheated vapor. Therefore, supercooled liquid is a metastable state in which the free energy has a shallow minimum and the system sits over there. But that is not the global minimum in the free energy. So thermodynamics will require the free energy to actually be there. That happens by a first order phase transition. In classical thermodynamics, you don't use the word, but in quantum physics, what you would say is that the system quantum mechanically tunnels from this local minimum of the free energy to this global minimum, and there is a first order phase transition. But if the experimenter is very careful, he can make water stick around in this metastable, marginally stable equilibrium phase for some time. Similarly, the universe is trapped in this metastable state. So the supercooled phase is a metastable state. It's a metastable state because it does not have an infinite lifetime, because there is a possibility of tunneling from this local minimum to this global minimum. Now, a similar thing can happen in the Guth phase transition. Particle physicists call this local minimum as false vacuum. It mimics a vacuum. When the universe is trapped in this metastable state, its energy density is dominated by a scalar field. I shall say more about it in the next lecture. Now, the scalar field, for all practical purposes, resembles vacuum energy. It is constant in space, it is constant in time, and it has a very large energy density. So when the universe is trapped in this metastable state or in this false vacuum, its energy density is dominated by the scalar field, which, as I shall explain next time, mimics vacuum energy. The energy density is constant. And so before the universe quantum mechanically tunnels from the local minimum to the global minimum and completes the phase transition, the universe will expand exponentially. And the rate of expansion will be e to the power ht, where h is square root of energy density, this time the energy density of the scalar field. So it will be exactly like this, except this energy density is not the energy density of vacuum, but the energy density associated with the scalar field, which is very similar to the energy density of vacuum in its properties. So let's show this picture once again. The scale factor is a function of time. There is an exponential expansion. This exponential acceleration is the inflationary phase of the universe. This occurs when the universe is trapped in this false vacuum, which is dominated by a very large energy density of the scalar field. And then there is a power law deceleration when normal physics obtains. Now, the important thing to appreciate is that this inflation, this exponential expansion, should begin and end very, very early in the life history of the universe. It should end by the time the universe is around 10 to the power minus 35 seconds. Because if this expansion persisted for a very long time, let us say if this expansion persisted till the universe was 3 minutes old or 180 seconds old, then all the other attractive features of the Friedman cosmology will be lost. In Friedman cosmology, because the universe was expanding in a decelerated fashion and cooling, we had the synthesis of elements, for example. Helium was synthesized, deuterium was synthesized. We will lose all of that. Therefore, this inflation, if it does occur, must begin and end in this period, from time interval between 10 to the power minus 36 seconds And it would certainly end by the time the universe is 10 to the power minus 34 seconds old. But the inflation, this exponential expansion, should last long enough to stretch the homogeneous universe again and again and again, so that the homogeneous domain of the universe becomes comparable to the size of the universe itself, and also to make the universe flat. In order for that to happen, the radius of the universe at the end of inflation, or the scale factor of the universe at the end of inflation, must be 10 to the power 33 times larger than the scale factor of the universe when the exponential expansion began. So we are not talking about a few e-folding expansions. We are talking of an enormous exponential expansion. So we are talking for long enough accelerated expansion to occur long enough so that the radius of the universe increases by 10 to the power 33. In other words, inflation should last for 75 e-folding times. The universe, as we shall discuss in the next lecture, possibly, the universe doubles in size every 10 to the power minus 35 seconds. Yes, you heard me right. The universe doubles in size every 10 to the power minus 35 seconds. That is why it is able to increase in size by a factor of 10 to the power 33. Now, before we discuss this inflation scenario a little further, I must digress into some basic physics. Now, I can leave it at that, but on the other hand, this basic physics is also some of the most beautiful physics that we know. And therefore, I cannot resist but try to tell you in simple terms. So in the next lecture, I would like to interrupt this cosmology story significantly to give you a feel for the following. What are phase transitions? What is symmetry breaking? The Guth phase transition is a symmetry breaking phase transition. So this is the paradigm of modern physics, symmetry breaking and phase transition. Third, elementary particles and their forces are described by what are known as gauge theories. And it is in these gauge theories that one tries to unify different interaction or different forces. What are phase transitions in the early universe? So these are the four topics that I shall discuss in the next lecture, and then I shall return to Guth's inflation, and then we will have the concluding lecture. So in the next lecture, I will discuss the interplay between the macrocosm, the universe at large, and the microcosm, the quantum world where the universe was 10 to the power minus 35 seconds old. Till then, thank you for your kind attention.